Morning. Can you hear me? So before I start, are there any questions from the last lecture? If not, I just want to clarify what someone asked me in an email, and then we can begin. So one of the things that I made use of was I just assumed that everyone will be happy with this. So if you have, say, I had psi 0 n h psi, and then there was a 1 acting on n, that this should give you e n 0 acting on psi together with psi, right? This being 0 and that one being 1. There was a confusion as to why didn't I put a 1 there. And the reason for that is that psi 1 and this was h0, right? So all we knew from the unperturbed part of the problem was that we knew that h0 was the eigen, that h0 acting on psi 0 gave you en0. We do not know what happens when h0 acts on psi 1. So what I'm saying is that the state psi 1, it's not really an eigen function of h0. The only thing that we know is h0 when it acts on psi 0, right? And the way that you do this is just that I just assumed that everyone was happy with the fact that h was Hermitian. So the way that you could do this was that you write this as psi n h0 psi 1 n. And as I was saying, we don't know what happens when h0 acts on psi 1, but what we know is that you introduce the Hermitian operator. So the Hermitian operator, by definition, it actually acts there. So this will end up giving you h0 Hermitian acting on psi n 0, then left with psi n 1. And now the Hamiltonian is Hermitian. We proved this, or if you want, for these simple cases that we have been dealing with, it is emission. So this h dagger is the same as h. So this will just give you h0 psi n 0 acting on psi n 1. And this, you just make use of this relation. So then you ended up, and n0 is a number, so you can take it out of the overlap. So you're left with psi n 0 psi n 1. So I just thought that I should clarify that was the reason why I kept saying that this operator is actually acting there. But if you wanted to do it formally, you have to introduce the Hermitian conjugate of h, let it act on psi n 0, and then get your result. Then the second thing that I realized was that in the second half of not the second half, the last part of the first lecture on degenerate perturbation theory, when I was going through the stack effect, for some reason I was muted. So will everyone, if I first explain that example? Today, the point of today is just to make use of the formalism that we derived in the first lecture to the hydrogen atom. So the stack effect is also an application of perturbation theory to hydrogen. The only difference is that here you set up you have some hydrogen atom, and then you said you put it in an electric field, not in a magnetic field. This is much simpler than putting it in a magnetic field. The point where we put it in a magnetic field, we have to take into account spin and all other effects. So I thought, let's just go through this example. So if you read the problem, you have used first order degenerate perturbation theory, calculate the energy levels of the n equals to 2 state of a hydrogen atom. Now, the first thing that we have to check would be is your state degenerate? So if you look at n equals to 2, so you know that hydrogen atom is labeled by n, l, and m. So if you have 2, if n equals to 2, then l has to go from 0 until you get to say n minus 1. So in this case, l can take values of 0 and 1. And m goes from minus l to l. So you know that the energy will be given by this problem. I called it the Rydberg number divided by n squared, right? The nth energy. So if n equals to 2, you know that E2 will just be minus 13.6 electron volts divided by 2 squared. Now, this energy doesn't depend on these other quantum numbers. So this will mean that the state that has 2, 0, 0, the state that has 2, 1, 0, 2, 1, 1, and 2, 1, minus 1. All these four states will have the same energy. So there is a degeneracy. So if you put this in an electric field, it might happen that this degeneracy will get removed or uplifted. That's what we want to do. And if you remember, for you to find what these corrections to the energy. So let's start by saying what is HP, right? Right. So you just put your thing in an electric field, so you know that this will just give you QE multiplied by Z. So I'm assuming that the electric field is pointing in the Z direction. I'll use this for the electric field because I don't want this E to be confused with the E for the energy levels. So you know that, as I was saying, there's a fourfold degeneracy. So this will mean that you have to first construct, because this is degenerate perturbation theory, you have to construct a 4x4 matrix, find the eigenvalues of those of that 4x4 matrix, and then the eigenvalues of that matrix will give you the correction to the will give you these numbers, the corrections to the energy levels. So you first have to label your states properly. So let's say that I will call the first state, this state I'm calling, this will be 2, 0, 0. Then the second vector I will call to be 2, 1, 0. Third vector I'm calling 2, I think maybe it's from around 2, 1, 0. So this means that the second one had to be 2 and 1. And then the fourth vector, I'm calling 2, 1, and the minus 1. Right. So you have these four vectors, then you form a matrix. So the matrix elements will involve things like H, say 1, 1. Right. So this will be state 2, 0, 0, HP 2, 0, 0. And then you have to go around calculating all these. There will be 16 of them. However, for this problem, you're going. So the best way to do this, if you are not sure about the arguments, it will be you just go around and you calculate all 16 matrix elements, but most of them will be 0. And the reason for that, let me argue, is that if you look at the parity, whether the final integral will be even or odd. So if you start with 2L m, say z 2L m prime, right? So let's just only look at the this is m. Let's just call it that m. Z is given by r cos theta. So it doesn't depend on the phi. So this will mean that this entire integral M and M have to be, will just give you delta M and M prime, right? So for now, let's just ignore that. So you are left with 2L Z. Now Z, it's odd, right? Remember that this is just a shorthand notation for the integral over r squared dr d theta d phi with sine sine theta. So Z will be odd, then you're left with 2L prime, right? Now, if these two have to have different parities, so that whatever you multiply, you end up with something that is odd. Then when you multiply it with that one, you end up with something even. So the only non-vanishing integral will be the one that will have 2, 1, say, I'll ignore the M, but the M's have to be the same. It's just that I'm ignoring them. Then you get Z 2, 0. Right? So this is the only matrix element that will not vanish. And if you compute everything, right, as I was saying, you have to first form this 16 by 16 matrix. Exactly in my notation, it will be this one and also this one. These are the only matrix elements that will not vanish. And then to compute them, you plug in the hydrogenic wave functions. So the integral you get r cos theta with r, let's see, this integral, which you can do. Then the remaining integral that might be difficult to do was this one. This one you can split it. I get r4 e minus r over a0 minus r5 e minus r over a0. And what are these integrals? You can write them in terms of the gamma function, right? You just do a change of variables. You can see that this gives you something like e. If you call this t, right, you get e to the minus t, t to the say 5 minus 1. So, and you know this is just an integral definition of the gamma function. So you end up with, if I write down everything, let me go back. So this gives you 4 factorial a to the 5 minus 5 factorial a to the 6 over 2a 0, right? And then once you simplify everything, you can see that you get something like 1 minus 5 over 2, which will give you that 3. There are normalizations, maybe a0, but the point is that you get this 3a0, which you put there, and then all we have to do then will be to diagonalize the matrix, which I did there, solve for the eigenfunctions. Once you have the eigenfunctions, then the set of these eigenfunctions, so you have will give you the corrections to the energy levels once you put them to inside an electric field. So the degeneracy has not really been completely lifted, because there are still 2 energy levels that still have some degeneracy. So it would have been completely lifted if maybe you got that thing that there was not 0. Right. And the other thing is that to get the correct good quantum number or linear combination of these things, you read these coefficients. So if you remember, I said that psi is going to be given by a alpha of psi n 0 alpha. right? Then you sum through alpha. These coefficients are, you get them from the eigen vectors. So maybe you got one of them might be 1, 0, 1, 0 with 1 over square root of 2. So you take these numbers and you form what the new wave functions will be. Right. So this, I covered this in the last lecture very quickly. It's just that I was unmuted, or I was muted. Right. So let's start with the fine structure. So what I want to do in this lecture will be to apply the formalism that we made use, that we derived, which is first order perturbation theory and second order perturbation theory, together with degenerate perturbation theory. Apply that to the hydrogen atom. So the hydrogen atom that we actually solved previously, it obviously there's going to be this mc squared. Then there was the term p squared over 2m plus the potential v of r. So this is what we did, I think, in chapter 4, when we solved for the hydrogen atom, when we solve for the wave function for the Schrodinger equation. So this, you can call this part of the Hamiltonian BH ball. But there are other contributions that we ignored, and the way to get this contribution will be to start with, which I will do in last lecture. You start with the Dirac equation, and then once you do a relativistic limit where then you get the original one that is solved in chapter 4, there will be other terms which I will derive. What I want to do just to compare the order of magnitude, which terms will dominate and which terms will be subleading. So other term which comes from relativistic corrections, because you know that from relativity that the kinetic energy is not given by p squared over 2m. It's given by an expression that I will derive, which will be p4 over 8m squared. I think this is c cubed, c squared, right? Plus, then there will be a term, the electron has been, the Schrodinger equation, for some reason, although it's a good formula, it didn't predict spin. As with the Dirac equation, the spin effects come very naturally. So the other term is called L dot S, or Russell-Sanders coupling. So it couples the spin of the electron to the orbital momentum, and there is 1 over R3. So this term and this one I will derive just maybe 5 minutes from now. What I want to do is that I want to find the order of the magnitude. So 1 over R cubed, 1 over 2m c squared. Right. Now, when you solve the hydrogen atom, you found that this term here, right, it gave you what we call En, which let's say that was given by half n squared m e4 over 4 pi epsilon naught squared, right? Which you can write this as, I think, it's of order alpha squared. Now, what is alpha? Let me define what is alpha. So alpha is just, there is, so let me just summarize what I'm trying to do. What I'm trying to do is that I'm trying to show that the Bohr energies are of alpha squared, and the fine structure terms will give you alpha to the 4. So what is alpha? Alpha is just, so the way that it was historically defined is that Sommerfeld wanted to generalize the Bohr atom to include relativistic effects, which is what we will be doing today, and also to include, there is no reason why the electron should be moving in circular orbits. So he wanted something much more generic. So you have elliptic orbits and stuff like that. But when he was doing this type of analysis, he realized that that there is a natural number which is a pure number. So if you find the speed that the electron is orbiting the nucleus, which you can call V1, then you divide this by C. What do you get? So you say, because mv squared, so the radius is just one Bohr radius, this will give you, what will this give you? What did I write on that side? This is just mv squared over r, so this is the m multiplied by a. This has to give you the force, and you know that the force is just coulombic, so you get 1 over 4 pi epsilon 0 e squared over a squared, so that cancels with that. So you're left with m squared, going to be given by 1 over 4 pi epsilon 0 e squared over a. And a, you know, is given by 4 pi epsilon 0 h bar m e squared, right? So that m will cancel with that m. So the ratio, let's say alpha squared of the speed that the electron is moving in the first Bohr orbit, that ratio will give you a pure number. And that pure number will be given by, you can read it off from what I wrote at the bottom of the slide. So that pure number is given by e squared over 4 pi epsilon 0 h bar c, because we're dividing by this squared, this number here, and this number works out to be 1 over 37 point something, and this number is called the fine alpha structure constant, and it's a very important number. But the problem is that no one really knows why it takes this particular value. And if you start changing this value, maybe you change it by maybe a percentage or maybe even 4%, you find that you start affecting the stability of matter. You start processes that should have occurred in, like, nuclear fusion. You no longer are able to produce helium, you're no longer able to produce carbon. So I mean, if you read Griffiths, I think it's one of the exercises, it says that if you can somehow derive this number without using this argument that I brought on to the speed of light, if you can derive this number from first principles, you can even get a Nobel Prize. But no one really knows why that number takes that value. For us, however, is that good thing is that this number is smaller than 1, because this number will form our lambda. It's what we will be expanding in terms of. So if you remember, you have a series expansion, lambda plus lambda squared plus lambda cubed with some numbers, right? And this, what I call the bookkeeping parameter, what I'm saying is that it's given by this alpha number. Are there any questions so far? Right. So first we have to find these hierarchies of these corrections. So the Bohr, that En that you calculated, 13.6 over n squared, you can show that is given by is of order alpha squared. Let's just see. Maybe if you write everything out, you get 1 over 4 pi epsilon 0 h bar c squared, I think e to the 4, and this is just alpha to the alpha squared, right? Now you have to compare the other corrections. So the first correction will be the relativistic corrections, divided by, in comparison to this one, right? So this correction gives you P4 over 8 m cubed c squared divide this by p squared over 2m squared, simplify everything. Remember, we're only looking at order of magnitude, so factors of 2, factors of 4, we are going to ignore, and p, if you use the classical limit, is just given by mv, so you get m squared, 4m squared, c squared, cancel, you get 1 over 4, but I'm not worried about the factors of 4 or factors of 2, so you get v squared over c squared, and that is what is v squared over c squared for the Bohr atom? I just spent 5 minutes explaining how that alpha squared, one operational definition is that is the ratio of the speed of the electron in a first Bohr orbit to the speed of light squared. So once everything cancels, I mean, if you get v squared over c squared, which is alpha squared. So this means that the relativistic corrections of alpha squared dominant than ER. So ER is already we calculated to be of alpha squared. So this will be, so what are the order of magnitude of HR will be what? Alpha 4, right? Because I've just calculated that the ratio between these two is alpha squared, so HR itself has to be going like alpha to the 4. And then you do the same thing for the other one, but maybe I'll give you that as an exercise, right? So now let's get to how you calculated this. So, you know, let me just repeat, right? You know that this equation p squared over 2m, this is not the whole thing, especially given that the electron in the first atom is moving with semi-relativistic speeds. So you have to make use of the correct relativistic expression for the energy. So we know that the correct one would be given by the energy is given by mc squared over 1 minus over the square root, but I don't want to be working with square root, so I will, okay, maybe I should first write everything down. So you get mc squared 1 minus v squared over c squared, square rooted, and that expression, and remember that this is the total relativistic energy, so it's given by, it will be the sum, but the mass is also some form of energy, so it's given T plus m squared. Remember that we want to find what is the relativistic expression for the kinetic energy, not in terms of the velocity. You've done classical mechanics, so you know that we're usually working with Hamiltonian, so in the Hamiltonian formalism, you have to express everything in terms, not in terms of, so the then would be in terms of the velocities. Here you have to express everything in terms of this dots. If you want it's q and p, you have to express everything in terms of p. So you know that p is given by m v over square 1 minus v squared over v squared. So you have these two equations. There's this thing with this q dot, which is the velocity. You have to get rid of the velocity. So the best way to do that is I squared everything. So you get m squared c4 1 minus v squared over c squared. Solve 1 minus v squared over c squared gives you m squared c4 over e squared. Similarly here, if I square everything, right, p squared will give you m squared v squared. You all have to divide by 1 minus v squared, and 1 minus v squared you have already solved from this expression here, from the expression for e. So you just, so this will give you m squared c4 of e squared. But we still have this v squared there. So you can solve for the v 1 minus v squared over 1 minus m squared c4 over e4 over e squared. This gives you v squared. right? Then you take this, you plug it into this expression here where there's that, so you get p squared will be given by m squared. Okay, the m's already cancel. You get e squared over c squared, v squared over t squared, which is given by 1 minus m squared c4 over e squared. So this gives you e squared over c squared minus m squared c4, right? And then you can solve this is equals to p squared. Now you can solve for what is, this is the final expression that I need, solve for e, right? And when you do that, you get e, right? This is what I did, just easier. And then once you solve for e, remember that e, from the expression that I wrote in the previous slide, you can show that, okay, let me write everything out. E squared will be given by p squared c squared plus m squared c4, right? Then you take the square root. This is the totality, so you'll have to find the kinetic energy, you have to take this energy and then subtract the rest mass energy. So this is the result. Is everyone happy with this declaration? You probably have seen it when you did the course in special relativity. Then the next step then will be to do an expansion. So I just t is given by factor out the c squared part, right? So if you remember, I said t was given by square root p squared c squared plus m squared c4. Factor out this part m squared, so you grab this as m squared c4 1 plus p squared c squared over m squared c4, right? This inside the square root, so you end up with mc squared times square root of 1 plus p over mc squared to the half minus 1, right? And then you expand, right? You remember from first year that 1 plus x to the n is given by approximately equals to 1 plus nx plus n minus 1 divided by 2 x squared plus dot dot dot. So this will give you mc squared 1 plus, right, you get the half p squared over m squared c squared plus, this will give you, this term is half times half minus 1 over 2, which will give you minus 1 over 8, right? And it's p squared over okay, maybe I should p over mc squared, that correct? Squared, it's this squared, right? So this should give you p to the 4. And once you simplify this, remember that I still have to subtract the mc squared, the mc squared. So this gives you mc squared, which will cancel the other mc squared, plus half p squared over m, right? The c squared cancels one of the m, and then, which is correct because this is the classical expression for the kinetic energy. And then the term that we were really looking for, which is why we started with these long expressions, was that we wanted to get what was the next order term. So this term gives you p to the 4 over 8 m cubed c squared, right? So I said this minus mc squared, and this is what we wanted. It's this term. Right? So if you were to write this down, what we have done is actually just the Hamiltonian for the Schrodinger equation will be given by the Bohr part, but there's now this extra term, which is minus P4 over 8 m cubed c squared. Then you can go ahead and try to apply perturbation theory, because you know that En, right, was given by this minus 13.6 over n squared. But now, because of this extra term, and if this term is very small in comparison to the other, and it definitely is, because of what I showed, that the relativistic corrections are of order alpha to the 4, whereas the Bohr part was of alpha squared. Alpha is a small number, 1 over 137, so it's a very small number. So this term here is small. So you can make use of perturbation theory. So this means that the shifted or the corrections to the first energy levels for the hydrogen atom. And this is a real effect, because if you go to the lab, you will find that the classic Balmer series, the spectral lines, if you look closely at them, you do find that they're actually splitting, even before you put them into a magnetic or an electric field. And this shift in the energies, you can measure them in a lab. So this is what we want to calculate. So you get psi n p to the 4 psi n. These are just the unperturbed, right? And this goes back to the question that I was asked. This P4 classically, or everything, any operator adds to the right, right? But unfortunately, or fortunately for us, you can check that P squared is emission. I think PR is the one that is not emission, but P squared is emission. So you can write this as P squared psi n 0 psi n 0, right? Because this is emission, it can add there. The other one, you can leave it as it is. So this just gives you P squared psi P squared psi. Right. So this part of the route I was explaining, this is just the perturbation, plug it into the first perturbation theory. Right. Now the Schrodinger equation. Now it's the same thing that I said yesterday. I don't know what HP. So HP could be some complicated operator, what I called H prime yesterday. I don't know what happens when it is on some generic state. So the same here, but you know from the Schrodinger equation. So the Schrodinger equation, if you write it down, P squared plus V, acting on psi, this will give you E. So you, from this Schrodinger equation, you can get what is the expression for P squared psi. It's given by 2m E minus V psi. So this means that you can rewrite the expression for the relativistic correction to be in terms of that 2m minus v, or let me just say this. Okay. As I said, the correction is given by psi n, psi 0n, h psi n 0. And maybe if you write this out, maybe let's say that for simple problem, this is just psi n psi of h, and this is a probability distribution. So this is p of x h dx, and this by definition, this is just the expectation value of h. So to do this, we have to find what is the expectation value of p squared, which is the expectation value of 2m e minus v. I think this is squared. Squared, I think. Right. So this will give you expectation value of n squared plus expectation value of V squared plus EV expectation, something like that. Let's see. Okay, that's what I just said. Maybe I can. Right. So we are there, but we know what is V for the hydrogen atom. So V is just given by E over 4 pi epsilon 0 divided by R. This whole thing is again just a constant. So whenever you want to find the expectation value of V, this is a constant. So you only have to find what is the expectation value of V of 1 over R. Similarly with V squared, you will end up, you square the Coulombic potential, gives you e to the 4 pi epsilon 0, 1 over R to the squared. So what are these expectations? Once you have managed to find what are the expectations, then you just plug them into this expression and then we should be, but how do you calculate these expressions? So I thought the easiest way to do this was to make use of what is called the Hellman-Feynman theorem. So the thing is that, let's just say that your Hamiltonian might be depending on some parameter, say lambda. This lambda could be R, right? Now, do a small change in this Hamiltonian, which will give you a perturbed Hamiltonian, right? So remember that H is given by H0 plus H prime. So the perturbed Hamiltonian is just the difference between the Hamiltonian and the unperturbed Hamiltonian. So I'm saying that H prime is just given by H minus H of the original one. So let's say that you have some original Hamiltonian that's depending on lambda. The Hamiltonian that then you look at what is lambda plus, let's say, some small change in the lambda, then you subtract the original Hamiltonian, which is just a function of lambda, right? And then if you do a series expansion, right, so this will give you, this is and delta is a small number, so this gives you H lambda plus delta lambda dH over d lambda plus dot 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 minus H lambda. That cancels that. But as I said previously, the expectation of this perturbed Hamiltonian, right, d H over d lambda, what I just showed, that this is just the first order correction, right? See, first order correction. Okay, so I've shown that H prime is given by d lambda from the previous slide, dH over d lambda. This gives you the correction. So let's say you started with H prime. This gives you this value here, which is some small delta E. So you end up, maybe it's just the correction to your energy. So this gives you delta E divided by delta lambda. This will give you the expectation value of the original Hamiltonian, derivative of the original Hamiltonian. And if you write this, psi n dH or d lambda psi n, right? So this is what we are going to make use of in order for us to get those expectation values of the expectation value of 1 over r and also 1 over r squared. So if you go back to, I think, chapter 4, whatever, when we're solving for the hydrogen atom, right? You know that you started with a Laplacian. This Laplacian had a radial part, r squared d over dr squared, third 1 over r squared, some angular part, right, we called L squared. Then you separated your variables. So you said that your wave functions will depend on R and some functions that depend on theta and phi. When they acted on that thing, they gave you L plus a half, which is that part, and there's a V of R then. So this, you can go back to, I think, the chapter when we were solving the hydrogen atom. There is this extra part there. And if you solve for En, this is just a second order differential equation. You do Frobenius method, and you end up with finding that En is given by this. Right? Now, if you remember that lambda is just a parameter, so in this case, I can take it be E. Although the value of the electron charge is fixed, I can make E to be a variable, and I can also make R obviously is a variable, and I can also make L to be a variable. So if I first say treat lambda or the electric charge as a variable, differentiate that, plug it into the Feynman theorem, dH by d lambda. In this case, it's dH over dE, right? dH over dE. H is given there, so it only hits there. So this will give you minus 2e over 4 pi epsilon 0. This is inside an expectation value, so I'm computing this thing. So I'm still left with 1 over r, which is what I'm looking for. But on the other side, if I differentiate En with respect to E, I just get this will give me e to the cubed, this equation. And this equation you can solve for what is 1 over r. So 1 over r is given by this. And recall that the Bohr is given by 4 pi epsilon 0 over is me squared. So in terms of the Bohr atom, this is just 1 over n squared multiplied by a. So to summarize, you've derived this expression, n squared a0. And then you do the same thing for the expectation for 1 over r squared. So let's see, if you wanted the expectation value for 1 over r squared, right, remember that the Hellman theorem tells you that if you differentiate dH by d lambda, this will give you dE over d lambda. So start by differentiating. Remember, we want r squared. We already have an r squared there. So I suggest that you differentiate with respect to L. So this is L squared plus L. Differentiate dH with respect to dL. You get something on the left side, you get 2L plus 1. This h bar squared over 2m, 1 over r squared. And then differentiate this energy with respect to L. This will give you me4 over 22 pi squared epsilon 0 h bar squared n plus L. With respect to L, this will give you a cubed minus 2. And then you can simplify because all the other parameters are known. Then write everything in terms of the Bohr parameter, Bohr radius, which is 4 pi epsilon 0 h bar squared over me squared. Right. So we find that in this case, and another thing, just for simplification, you saw that when we had L plus 1, which was L squared plus L. When we differentiated, we get 2L plus 1, which you can simplify to L plus a half, which is this part here. Just do everything right. So I'm saying that I factored that L plus a half, that 2 cancels that, everything simplifies into this expression. What we were doing, this because we had things like 8 minus v squared, expectation value, En squared. We had to find the rotation value of V squared, which involved an R squared, involved an R, plug them into our result, and it's a bit messy. This is R squared, I think. Right. So remember that I expressed everything in terms of the Bohr radius. This is the expression for the Bohr radius. Then you're going to get this En was just coming from when you expand E minus V squared, right? You will get some term there. Then you make use of the fact that En, if I get my things correctly, En is given by En squared over 4, it's 4 pi epsilon 0 h bar squared, right? So 4 pi epsilon 0, 4 pi epsilon 0 with an h bar squared, e squared, e squared. This gives you another extra factor of En, right? Similarly, for the other terms, if you simplify everything, you get En squared. So you can factor out this factor of En squared. So you get En squared over 2 c squared. Right. This terms gives you the minus 3. The other one you just leave as L plus a half. Right. So this is the first correction to the hydrogenic wave functions, but we're not yet done. So the fine structure consists of 2 parts, right? H fine structure. What we've calculated for now is the energy due to the relativistic correction, which is that we're using the wrong expression, P squared over 2m. The expression that you had to use was the E squared equals to P squared stuff. We've found this expression. Now we have to find the second contribution. The second contribution is coming from the fact that the electron has spin. So that's the, what didn't I include? Okay. Right. So let's start. So you know from first year physics that the energy, so the electron will be spinning around, but any charge that is moving will set up a magnetic field. So we know that that energy of that magnetic field will be given by, I think this minus the magnetic moment vector multiplied by the field. So first I have to find what is this field B. So by using Biot-Savart, again, this is first year physics, you get mu naught. There's going to be some current element multiplied by R over, I think, R cubed over 4 pi, right? And J is going to be given by mu naught over 4 pi, then by E V cross R over R cubed. Now E is given by 1 over 4 pi epsilon 0. So there's epsilon 0 there, epsilon 0. E over R squared with R then. So this simplifies to mu 0 epsilon 0. This 1 over 4 pi with the E with an R squared there, this gives you an E. So should I before I go there, right, is before I simplify everything, right, is what is this number here? So the famous, yes. So this was one of the most famous expression by Maxwell. So if you go back to 1864, Maxwell was studying equations for electricity, equations for electricity, which were due to Gauss biosava, and also magnetism, he found that he could write these equations in differential form. From those differential form, he had something like dE squared, I think 1 over c squared, d2 over dt squared, with a number here. That number, if you do it properly, v is given by, I think it's 1 over epsilon 0 mu 0 with a square root. And once he plugged these numbers into there, he found that this was 3 times 10 to the 8. So, which convinced him that these were indeed, that light was a form of these electromagnetic waves that he was seeing. So this is 1 over c squared, right? Then I leave the v as it is. This cross r with r squared with 1 over 4 pi, that's just the electric field. So the magnetic field is just given by, I think might be missing a factor minus, but I'll check. It's given by 1 over c squared v cross e. Now let me just multiply everything by okay, and you know that QE, this should give you the force, and the force, if is might be given by dV over r, it's given by the gradient r hat. So you are going to end up having to replace the electric field by dV over dr. So and given that, so I think I skipped some steps. There's a dV over dVr L. So this is the magnetic field. Is given by dV. I should say it's proportional to the magnetic. I'm not doing this. You saw that we had this vector v, right? Just multiply this by v. There's r somewhere. Divided by mv. This is just the angular momentum. So you can express everything in terms of the orbital angular momentum. So we have this b. Now we just have to find what is the mu for the electron. So mu from first year, you know that mu is just given by the current multiplied by the area. So the area here would be pi r squared, right? So then this will give you, I think it's E divided by the period, pi r squared. Period will be given by, I think, 2 pi, just equals to VR, right? So, no, not VR, VT multiplied by the period. So the period is just 2 pi r divided by that v there, right? So the pi's cancel, so you're left with E v r, right? Everyone happy with this expression, EVR. Okay, let me just go back and just assume that for the moment that the charge is given by Q, right? You end up with this is classically the, if you're not happy, you can go back and look at your first year textbook, but it's given by QVR. Now, you want to express everything in terms of the angular m is by m. So this gives you Q, let's say angular momentum. I'll just, for now, I'll use L divided by m. So you have this result, which is a classical result. Quantum mechanical result, it's similar. So Q in this case would be minus E over m multiplied by the angular momentum. So what's happening here is that the electron seems to be spinning around the, I'm using the wrong diagram, but it's spinning around the the nucleus, ZE, but it's also, even though this is a bad picture, it's also spinning around its own axis with angular momentum S, which is this picture that I'm using here. So you will naively think that is something, the picture is wrong because the electron, it's a point particle, so this picture doesn't really hold. But similarly, but the thing was that there's a vector here, which is given by this G, famous G, the G factor. So the G factor for the electron is not true, but let me be precise. The Dirac equation will give you a factor of 2, but there are other numbers here, so which are called the anomalous magnetic moment of the electron, which has these factors, but it's just true. But for us, we're just going to assume that the Dirac equation is accurate, so we are going to take it as true. So yeah, I asked if everyone was happy, and you let me write the wrong thing. There's this factor here of 2. Is everyone happy that there was a factor of 2 here? It's 2 pi r, so it didn't cancel. So classically, there's a true. Classically, there's a true. Classically, there's a true. Just redo the calculation and make sure that there's the factor of 2 there. Quantum mechanically, the same expression will hold, only that there will be this fudge factor of G, which works out to be 2 in the Dirac theory. But it's not really true. You have to, yeah, I think I'll have to go back to the table with a shift to explain what happened with these numbers. But for now, if you just assume that this factor is true, right? So this is true from the Dirac equation, you end up with that. This is just given by e to the minus m over s. Then you can plug everything, and so this is coming from d. This comes from taking derivatives dv over dr, right? So we are left with this as L term. So this is sometimes called Russell-Sanders coupling term, but I'll just call it, yeah, spin orbit coupling. Now this is another part of the Hamiltonian. So to find the corrected energy levels, E, this has to be, you have to calculate the expectation value of 1 over r cubed s dot L. Right. The expectation, okay, so this is dodgy, but let's just say that this is what I have to calculate. I have to calculate 1 over r cubed. Then I have to also calculate the expectation value of s dot L. The expectation value of 1 over r cubed, I go back to the Hellman-Feynman theorem. So it should be easy. Right. I want to differentiate this such that I get the h over d lambda. I get something that will give me an r cubed. It's easy because if you look there, right? So what should my parameter be in this case? I need some parameter so that I can differentiate h with respect to that parameter, so that I end up with 1 over r cubed, which is the expectation value that I need for the S spin orbit coupling term. Okay, the parameter has to be r, right? Because if you differentiate the h over the r, this is an notation, it will hit this term, right? This is r cubed, so you end up with h bar squared over 2m. Differentiate r squared, you get r cubed, but it's inside an expectation, and there will be some numbers. But now you have differentiate the 1 over r there, you get 1 over r squared, but the expectation value for 1 over r squared we actually obtained. So this gives you L plus 1. So just remember that there's an L and an L plus 1, so you can get that R, the expectation value of 1 over R cubed, is going to be given by whatever you got for R squared, but there's going to be L plus 1. There's going to be, yeah, just do it properly, and I'll go back to the expression that I got. You calculate the expectation value for this expression, right? So the L times the L plus 1, I just explained where you got that one from. The L plus 1 will get from, remember you are relating this to the expectation value of 1 over R squared. So that will come with an R cubed. Then you plug this into that term. This will give you the denominator, this term in the denominator. But we still have to find what is S dot L, right? Or, now the total angular momentum is actually conserved. So not only conserved, it's actually a good quantum number. So if you square that number, K squared, L squared plus S squared plus 2L dot S. So you can solve what is L dot S. So L dot S will give you half J squared as operators plus, I think it's minus L squared as operator minus S squared. Right. This gives you the expectation value, and if you work it out, the expectation value is basically J squared acting on LM, or maybe JM. You know, when this acts on this type of stuff, you just get J times J plus 1 with an H bar squared. So you replace, yeah, this will give you the expectation value for S dot L, this one. And then you plug everything, S is half, so you end up with this expression. Now, as I said in the previous slide, because of time, you can check that this simplifies to something like that. But the point is that you have to add, right? So the fine structure, the corrections to the fine structure, they are due to the relativist corrections, which we computed previously. Remember the minus 3, I think it was L plus a half, which is J. And then this simplified in the previous slide. So adding everything up, so you can put a J plus half there. This 3, you leave it as it is. Put J, I might as well do this. Let me erase everything. Right. Just do some algebra. So leave the 3 as it is. Then you get J plus half, J plus half. So this gives you nj, which is this one. For n times a half will give you minus 2n, which cancels with that 2n. So they cancel. So you're left with minus 4nj. The j's again cancel. And then you're left only with that this gives you en squared over 2mc squared 3 minus 4n over a plus half. This is the final result for the fine structure contribution to the energy levels, and this is alpha squared, right? So maybe I think you get something like En plus alpha squared En of 3 minus 4n over j plus a half, which, and this is the energy level up to order alpha squared in the fine structure constant. So I think we can take a break. Just, I'm not sure how long you want the break to be, because I'm done with the first lecture. Maybe 5 or 10 minute break, 10 or 15. Okay, I suggest we have a 15-minute break then. So everyone happy with that. Okay. So we might, okay, let's say we start at 10. If everyone is free, it's happy with 10, we can start at 10. Anyway, the okay, cool. Stop recording.